Hello everyone, I'm Mark Herndon and I'm going to walk you through my final project for NYU Poly's CS6963 Digital Forensics. The original goal of my project was to create a file carving utility that was specifically targeted at extracting data from a compressed NTFS file system. As you probably know, NTFS has built-in support for compressing files, folders, or even entire drives on the fly. And once the data has been stored in that compressed format, it becomes nearly impossible to analyze or extract using conventional forensics tools. So I saw that as a hole that I might be able to contribute to filling, and after looking around a bit, I found a number of digital forensics sites that agreed this was definitely a topic in need of research. The compression algorithm used by NTFS is called LZNT1. It's a proprietary variation of the standard LZ77. And since my original intent was to specifically target that algorithm on NTFS file systems, I called my project LaZy as a play on the name. As I say here, Microsoft doesn't publish the specs for their algorithm, but a number of engineering teams have gone in and reverse engineered the behavior well enough to reasonably understand how it works. In my opinion, the best such resource is the manual for the Linux NTFS file system driver. I've included a link to that here. And also, I previously published a Sci4 module that covers the technical details of the algorithm. So if anyone's interested in learning more, I'd recommend actually starting with those resources. In the end, my project grew in scope considerably once I got over the initial hurdle of actually carving data from a compressed volume. First, I was able to remove some of the NTFS-specific design choices that I had made. This allowed it to work as a more typical file carver on other file systems. I was also able to make it auto-detect between compressed and uncompressed data stored, mixed into the same volume. Even though the original goal had been to process images where the whole file system was compressed, this allowed me to support the other cases where maybe individual folders or just single files were stored compressed inside an otherwise uncompressed volume. And then the big feature I added at the end was a rudimentary bulk extractor type capability, so that in addition to carving files, it's also able to read out email addresses, phone numbers, and other data patterns, even if they're buried deep inside a compressed file. So I figure that's enough talking about the project. I want to spend the rest of my time showing you what it can do and how to use it. You can see here that I've published the project to PyPy, and there's some basic description as well as installation and usage instructions. The easiest way to get started is to actually install it through pip, so that's what I'm going to do here. We'll just call pip and tell it to install. What you'll actually notice once I get it going here is that it's going to automatically detect and install some dependency modules as well. None of those dependencies are actually required. In fact, the only benefit they add is metadata extraction on various types of files that get carved. All of the meat of the code that does the real analysis and the carving work, that's actually original and it's not built on or dependent on any other resources. But you'll see it goes ahead and finds all of these dependencies and automatically installs them anyway, just as kind of a bonus. We're going to let it go ahead and finish here. Just takes a moment or two with all of those metadata modules. Okay, looks like it's just finishing now. So now that it's finished, I'm going to open up this little program. This is a little launcher that I wrote. You can see all that it does up at the top here. It takes user input from argparse, and then it basically passes that into my program. It instantiates an application and tells it to run. You don't actually need a launcher like this. There's other ways that I've documented to interface with my project, but this is going to allow me to demonstrate some of the advanced features that we've talked about, and it was just the easiest way to do that. So we're going to go ahead and switch back to the console here. You'll see this is an empty output directory where the project is going to store its outputs. And we're going to go ahead and just tell it to run with the default options. We're going to run that launcher program on a file called compimage. Okay, so right away we'll see here it's found a few files. There's an MBR at the top, of course. There's some bitmaps, some Word documents. Normally you'd just let this run. It would take a couple of minutes to process the full image, but what I'm going to do, I'm going to give it another couple seconds, let it find 2 or 3 more files, and I'm going to go ahead and break it early. In fact, I think that's about enough now, so we'll just do Control-C to break. You'll see over here in the output directory, this is where it was saving off the types of files it found, as well as, of course, an audit log. The audit log contains information such as where in the image the file was found, the length, MD5 sums, and of course whether or not that file was stored compressed inside the image. Because as I said, here's a perfect example. Here's a PDF that was not compressed that it was able to extract, while most of these the Word documents, the bitmaps, they were of course stored compressed. So the tool's able to differentiate that and carve the data regardless of compression state. Also, if I go ahead and open some of these files, maybe just pick one of the random bitmaps or something, you'll see that in fact these are proper files. They were decompressed and carved properly. Oops, that one opened up off screen. Here we go. Here's just that Word document that we just opened. So that was the basic capability that I was aiming for, just to decompress and extract data off of a compressed file system. But rather than leave it there, I want to show you some of the advanced features we mentioned earlier. I have to actually delete all of these files or it will complain about a non-empty output directory. And we're going to go back to the console here. This time I'm going to add a couple options. We'll point it at that same image. What I'm going to do, I'm going to add double carving. I'm going to add the ASCII extraction that we talked about earlier. And I'm going to add post-processing for metadata. Okay, so this one, as you can see, is already producing a lot more output. And this one I'm going to let it go ahead and run through to completion. While it's running, I will mention a couple of the other post-processing options that my tool implements. First, you can validate certain file types after they've been carved. So for example, if maybe it carves a Word document, but then later it goes back to validate it and it realizes it can't open that file, it'll actually delete the file. It'll keep the log entry, but it'll mark the log entry that that file was found to be invalid. So you still have that data in the log, the start offset, the length, the MD5 sum. If you wanted to go back into the image manually and analyze that area of it, but whatever's there basically wouldn't be openable in Word. In fact, whatever's there is quite likely compressed, and even if you manually decompressed it, whatever you would get out wouldn't be openable in Word. It's just a way to clean up files that it thinks are maybe false positives. Another thing you can do, you can tell it to clean up all these weird intermediate files. You see where it says found file of type ASCII raw, and you'll see a lot of that scrolling by. The reason behind keeping that data by default is I thought it would be useful to have my tool decompress a bunch of raw data, save it for you, and then you could let a more sophisticated tool, for example maybe bulk extractor, dig in and find things that my tool isn't designed to look for. But if you weren't going to do that, you could tell it to go ahead and clean up those ASCII raw files for you and only save the useful outputs, which you can see a couple at the top of the screen. There's some URLs and some phone numbers, things that it was able to extract out of that data. Well, it's still going here. Shouldn't take too much longer. Alright, it looks like it's finished now. We'll go ahead and open up the audit log. And here this time you'll see the very first file as an example where it was able to extract some metadata. It does support most graphic file types, bitmap, JPEG, TIFF, that type of thing, as well as Microsoft Office documents, both the old and the new formats, as well as PDFs, and a couple others I'm not quite remembering. In addition to the audit log, you'll see these new files that were added for emails, phone numbers, etc. If I go and open one of those up, you'll see here this is the list of email addresses it was able to extract from the file, as well as where in the image file that was found, and of course the name of the image. Remember, of course, that this data was stored compressed, so the actual data at these listed addresses probably won't match what's here at all. But this is in case you wanted to go back, maybe tie one of these strings to a file that was also extracted near that address. This would give you the information necessary to do so. At the bottom is a histogram report. This is pretty similar to what Bulk Extractor provides. I just put everything all in one file instead of in separate files. And you can see that different representations of the data are handled. For example, some of these have angle brackets around them. That didn't confuse the parser. If I were to open up the phone numbers file as another example, you'll see there's some different amounts of spacing, hyphenation, parentheses. Some have none at all, some have all of it, but it's able to see through that. There are some false positives here I guess I should address. For example, this 555 number. All I can really say, this is a more intelligent search than just a generic, print me out any sequence of 7 numbers in a row. If I had done that, there would have been dozens, maybe even hundreds of occurrences within this image. And you can see for the most part it's able to ignore those and reject those false positives for you. Definitely one or two seem to have snuck in here, but nothing's perfect, right? Okay, so back in the output directory, at the top here you'll see folders for raw data that was extracted because my program thought that the data was interesting, but it didn't match any specific file type. These are created actually by the double carving and ASCII extraction options that we enabled. Each one does have its own type of log, so if we open up the ASCII log, you'll see here, we'll skip through it. Actually, I'm going to skip all the way to the bottom. You'll see some of these chunks of ASCII were not compressed. You see where it says false, false, false. Others were compressed. So again, it was able to, find some raw ASCII that it thought was interesting, and it was able to find some other compressed data that it thought was interesting that happened to then later decompress into ASCII. In fact, I want to call your attention specifically to this last file. This is the type of thing that might stick out to an investigator. You can see it's 60K of pure ASCII. It was stored compressed originally, but as I said, it doesn't match any type of a file signature. So, maybe this might be the body of an email or just a normal text document, for example, something that's not a Word document or something that would have a signature. So that seems like an interesting file to look at, number 492. We'll go ahead and open that one up. It's all the way at the bottom here. And it turns out that this is actually a C program. So this is the type of thing you could never have a file signature for. I mean, I suppose you could maybe look for a pound include statement or something to trigger you that this is a C file, but generically there's really no good file signature for a C document. And you'll see that this entire program was extracted, I should say decompressed and extracted perfectly. So I thought this was a pretty neat capability, even though the vast majority of these other raw files, I can tell you, they're not going to be nearly as interesting as that one was. It's just kind of neat that the tool can make a decision as it's going through. It sees what looks like a random chunk of data, but it'll make the decision that maybe that chunk looks a little more interesting than just purely random data. It'll go ahead and attempt to decompress that data, and sometimes, like here, you'll end up with something usable. Okay, so back in the main output directory here, you'll see a number of these folders end in an underscore. And that's actually the indicator for the double carved files that I said we'd come back to. These are files that might have been found inside another file type, maybe a JPEG that was inside of a Word document, for example. So it gets extracted out separately, and we mark it with the underscore indicator. And this is good just in case maybe the Word document as a whole couldn't be extracted in such a state that it was recoverable and usable, but maybe just that inner portion, a JPEG that happened to be in there or some other type of content, maybe that was able to be extracted and still usable. So it's just a way to, like I say, double carve the data. If I actually open up a couple of these and open up the JPEG, I'll give you a JPEG and a PNG, you'll see that's actually not the case this time. This JPEG shows very heavy corruption. It wasn't able to be recovered successfully, and the PNG here will show is pretty much exactly the same. But one example I want to show you where it did work would be this HTML document. You see with the underscore here. We open that up and you'll see this is a perfectly valid HTML document that was able to be recovered. And now if I go back and close it, I just wanted to point out, you'll see there is no other HTML folder here without the underscore. So this is not a duplicate file. It was not carved twice. And more importantly, it would not have been carved had we not been running with the double carve option enabled. So I guess with that, I've gone through the crash course of how to use my project and what it's capable of. You might loosely summarize it as a combination of scalpel and bulk extractor that happens to work equally well on either compressed or uncompressed file system images. In the case of everyday uncompressed images, I trade blows with scalpel pretty equally. I've done some tests back and forth just to make sure that I'm on par with its performance. And of course, I don't provide nearly the capability that bulk extractor does. That wasn't really the original intent here. That was more of a bonus feature that I threw on, but I still feel it's very useful. And of course, neither of those tools can operate at all on compressed data. And my tool has the convenience factor of providing both of those forensic capabilities in a single package. And I did mention before, of course, the tool can be used to decompress raw data, which you could then feed into more capable tools such as bulk extractor, and that way you get the best of both worlds without me having to try to beat them at their own game, if you will. I can do what I do well, which is to compress data, and they can go through and attack it all day long. So I hope you've enjoyed the presentation and found this useful. I had a good time demonstrating it for you guys. Thank you very much for your attention.